Hello, good evening, and welcome to the week 8 live session. Hope you're able to hear me and see my screen clearly. We'll get started now. So, again, there were a couple of doubts last week. I think I answered some of them in the discussion forum, and then maybe another one was asked in a personal message. But I'll briefly talk about both of those in case others have those questions as well. And then we'll move on to this week's questions. Okay, maybe I'll wait a few more seconds before starting. People are still joining. Okay, let's get started. Yeah, so the first doubt was, I think, asked in the discussion forum. So I'm not talking about the doubt itself again, but I want to emphasize this idea of kernel decomposition, right? So I think this is a modified example I've picked up from one of the course lectures I found, which was probably, I wanted to share that also with you guys. Second. So the original content from which all of this is taken is, I think, the CUDA webinar on parallel reduction and reduction kernel optimizations. So I think the course material for this week 6 or week 7 also, and many other GPU architecture courses, follows this very closely. But I think I found one other resource that had kind of slightly modified these images and illustrations for better understanding. I'll share that also, and I actually meant to put it into this slide. Let me do that. Yeah, so you can refer to this for a better understanding of these concepts. So basically, with regards to kernel decomposition, I think some of you had doubts on what happens. We say that, okay, a certain number of blocks are launched in the first iteration. After that, what happens? How many elements are left, and so on, right? So this whole idea of kernel decomposition, again, because of the way CUDA is designed and because of the way GPU architecture is that you cannot have synchronization among blocks. So instead, what you choose to do is to break down the computation into multiple kernels. So each block that, as you see here, so these are numbered. So you can see that there are 8 blocks in this level 0 doing this tree-like reduction on some number of elements, right? Again, depending on which particular reduction kernel you're talking about. For instance, last week there was a first add during load variant where you would launch half the number of threads as the number of elements, right? Depending on that, you may have whatever number of threads and blocks. But the key thing to remember to calculate how many number of elements are left after each iteration is that basically every block will work on its set of elements and reduce it to one single element. So you can notice here that there are 8 blocks and ultimately you're left with 8 elements. And then in the next level 1, you launch how many ever blocks are needed to process those 8 elements, and you are left with, here you only launch one block, so you are left with only one element. So this is what I think that some of you were confused about, because once we get into the reduction kernels, we don't talk about this part explicitly, right? In all your examples, you talk just about what each thread will be doing and things like that. And in contrast, your assignment and exam questions ask how many blocks are going to be launched or how many iterations will this take, right? So there was that disconnect, I think, for some of you. So hopefully this is clear. If you have any further questions on this, please feel free to ask on chat. Okay, only difference between first add and other reductions is that when loading the values from global memory, only half the values are loaded in shared memory. I think there were some other improvements as well, right? Maybe you can refer to the course slides and see. Yeah, there may or may not be other advantages. I don't remember it particularly. I can look at it and tell you in the next class. Sure. Any other questions? Stride and coarsening factor with respect to thread coarsening. Okay, got it. Yeah, I think we have some questions on that today. But yeah, I've not put that explicitly in the recap. So Uh, we can we can see. If I have a little more time, then I'll talk about this today itself. Otherwise, I'll talk about it in tomorrow's in the next week's live session. But yeah, this question is also I've noted it down. Okay. The other doubt I think some people had was again about this question we talked about in a couple of weeks ago, right? Whether you're certain when you have TIDX and TIDY as certain values, whether your load transactions have bank conflicts or not. So again, I've not gone into detail here, but the way to solve these questions are, first of all, you have to understand how the data is mapped to the shared memory, right? So for instance, in these questions, I think you had a tile of X and Y. So you need to figure out how that is mapped to the shared memory. As in, I think in this case, every column was mapped to one bank. Then secondly, what you are trying to access here, right? So I think the expression was style of TIDY, TIDX, right? And then finally, what if you set these values to something, what is a pattern of access, right? So we also discussed about how these warps would be formed, what are their thread IDs, Y and X going to be. And once you do all of those things, you'll be able to map this to figure out which banks the access will be from. So for instance here both are X, so you will be accessing elements in the form of 0 0 0 1 1 2 2 and so on, which is sort of like a diagonal axis. Now once you get this, you have to go back and map it to how is the data mapped to the shared to the banks. So again remember, every column of the data was mapped to one bank. So by default, these diagonal axes will go to different banks. So there would be no bank conflicts, and that's why the answer is false when you say have bank conflicts. So I hope these conflict related questions are also clear now to everybody. If not, please let me know and we can discuss them once more. But yeah, this is how you solve them. Yeah, I think that's all I had on doubts. So I'll pause here for a few seconds. If you have any other doubts or questions, please let me know. Okay, if not, let's move to week 8 content. So broadly in week 8, we look at different ways of doing kernel fusion and different ways of doing coarsening, right? So coming to kernel fusion, we looked at three main types: inner thread, inner block and interblock. And coming to coarsening, we looked at thread coarsening and discussed what coarsening factor is in that context. Similarly, we looked at block level coarsening and we also discussed stride length and what it means. So we'll look at a quick recap on some of these topics and then we'll move on to the problems. And I think a couple of you had also asked other questions maybe in the last 2 days in the discussion forum. But so problem with installing CUDA, I think somebody had asked and attached the error. So I think the regular TAs would be able to answer that better. Again, there was I think an assignment question also. That also I think they would be able to answer. So I don't think there's anything else from the live sessions part. Okay, so let's get into the recap for this week. So loop fusion is a typical compiler optimization. It's not specific to GPUs, right? You may or may not have heard of it, but it's a very basic compiler optimization. So you basically want to improve performance by doing various optimizations, right? You reduce the cache misses and then you reduce the branching and so on. So what it broadly does is fuse iterations of different loops when those iterations reference the same data. So here you can see two for loops, for instance. Here the data reference part may not be true, but this gives you a very simplistic idea of fusion, right? So you have an AI equal to something, BI equal to something. You can simply rewrite this loop as a single loop which does both those instructions. Again, it will save you some amount of, it will give you some amount of a performance benefit. Now, in the context of GPU, again, this kind of loop fusion is it translates to what is called kernel fusion. So again, if you look at deep learning frameworks that are there today, for instance, NVIDIA provides TensorRT for inference. You'll see that one of the optimizations that TensorRT says it does is kernel fusion, again for better performance. So here we look at what is kernel fusion and what are some of the ways you can do kernel fusion. So here, why you apply this to a group of GPU kernels. Why do you do this? You increase efficiency by decreasing the execution time and the power consumption. And once you have launched it into the device, you have no control over how they are scheduled. So kernel fusion is kind of what you do from the host side, right? So you redefine the kernel, or you kind of merge two things and so on, and then launch them. And kernels using the same or different data arrays can be replaced with a single kernel call, which basically, again, like the simplistic example we saw, it aggregates the code segments of the separate kernels. This is the broad idea of kernel fusion. Why do we do it? Again, it increases efficiency broadly. How does it do that? There's data reuse using on-chip memory. There's, again, as a consequence of this, there is reduction in off-chip memory traffic. It reduces global memory data transfers, reduces kernel launch overhead. So for instance, by launching a single kernel, you may be doing the work of two kernels, right? So the overhead, or the amount of work that you do per kernel launch, increases, and the kernel launch overhead decreases. And you may be utilizing more threads in the GPU as well. So those are all the advantages. But there are also limitations. And why do those limitations come in, right? So there are some architectural constraints, like the capacity of on-chip memory or registers. So if you try to do fusion, your memory requirements may increase, and that may cause problems. And reduction of off-chip memory traffic, again, is possible to a certain limit. And further, you have to actually identify these kernels that can be fused. And further, after you identify that it can be fused, you have to kind of come up with this method that can optimally rearrange these fusible kernels. So all of these are overheads, right? Instead of simply launching them, now you're trying to do all of these extra steps. And again, as a consequence of this, it may introduce warp divergence, which, as we know, again causes degradation in performance. So kernel fusion is something that can help, but it takes some amount of overhead in doing it also, and it depends on the architectural constraints. So very simply speaking, so here you have kernel 1, kernel 2 and kernel 3. Three different kernels that do various operations. A and B are your inputs here, and C and D are the outputs of these two kernels, which further serve as inputs to K3. And then you finally have an output. This is your unfused or naive kernels. Now you could fuse all of these together, K1, K2, K3, to form some new kernel called KF. And notice that here everything was using global memory, C and D, A and B, and your outputs. Whereas now you could use local memory for the output of K2 and shared memory for the output of K1. And then only your final output will be global memory. So this is one example of kernel fusion, very broad sense of it. We've still not gone into the details or how do you do this fusion. So now coming to that, as I said, we have three types: inner thread, inner block, interblock. So pay attention to this, because most of the questions today will involve your understanding of these concepts very well. So even if you've watched the lectures, that's why I put these in the recap so that you remember again. So in inner thread, it's a very simple concept, right? So like the first example that we saw where you had two for loops and you kind of put statement 1 followed by statement 2, inner thread fusion is somewhat similar. Every thread is going to do the work of kernel 1, then the work of kernel 2. So that's inner thread fusion. It's a very simple form. So broadly going over it, combines the computations of two kernels into a single thread, and it is suitable for both dependent and independent kernels if the data space size is the same. Now STH is the number of threads in a thread block, SBK is the number of thread blocks in the kernel. Now how do you come up? So first question in this fusion is, how do you come up with the launch parameters for this new fused kernel, right? Because your launch parameters for kernels 1 and 2 may or may not be the same. So in each of these techniques, you'll see a different way to do that. So here what you do, you take max of the number of threads in both kernels, max of number of blocks in both kernels to come up with the threads and the blocks. And this is not suitable if you don't have an equal number of threads or block. Again, it could result in things like different threads doing different amounts of work and so on, right? So if both of these are equal, then you're basically, when you kind of do this fusion, every thread would be doing the same amount of work. But if you have, let's say, 5 threads in one and 10 threads in the other, then you may have this situation where the workload is kind of unbalanced between the two. So that's why we say that it's more suitable when the number of threads per block is the same and if the data space size is the same. So coming to an example, so notice that there is K1 and K2 here, and here your K1 and your K2 have the same dimensions as can be seen. So you have 2 threads and overall 6 blocks, and it's the same here, and you do the max here, which turns out to be the same as the other two. So it's very simple, right? This is inner thread fusion. Now coming to the next type, it is inner block fusion. So here what happens, in a given block, certain number of threads do the work of kernel 1 and certain number of threads do the work of kernel 2. So very simply, if you had to look at it logically, if your local thread ID, that is the thread ID within a block, is less than some x, you do the work of kernel 1. If not, you do the work of kernel 2. That's the idea in inner block fusion. But again, we have to come up with the threads and blocks for this method also. So here, what you're doing is you're taking the computation of two different kernels and you're distributing it among threads in a single block. And this is suitable for independent kernels with small block sizes. So again, STHI and SBK remain the same definitions. So now there's a small change here. The number of threads is the sum of threads for kernel 1, threads for kernel 2. Again, why is this? Because this is how you distribute the computation, right? So if one of the kernels needs 4 threads per block and the other needs 8, it's good for you to have 12 so that same structure can be retained, because 4 of your threads are going to do the work of one kernel and 8 are going to do the work of the other kernel. Whereas with respect to number of blocks, we don't take sum, we just take max of the blocks that are there for both the kernels. And this is not suitable if STH exceeds the upper bound, because you're doing a sum operation. So even though the individual number of threads per block in both the kernels is within, let's say, that 1024 or 2048 limit that the architecture imposes on you, the sum of the two may exceed that. Then this method will not be suitable. Again, if kernels have a synchronization statement, that also will not be suitable, because you can't have a kind of partial synchronization. So here is an example of inner block fusion. So here are two kernels that you have in their unfused form, and the pictorial representation of the fusion looks like this. So in a given block, you're going to have 3 threads that are doing the work of K1 and 3 threads that are doing the work of K2. That's why the sum of the threads becomes this plus this. The blocks remains the same. In this case, both of them have the same number of blocks. So here also the same number of blocks will be retained. Otherwise, it would just be max of the two. So that's inner block fusion. And yeah, we discussed this. Partial threads, and therefore there's synchronization for partial threads is an issue. So that won't work. Now the third type is inter-block fusion. So here the computation is distributed among the blocks itself. So some blocks will do the work of kernel 1 and some blocks will do the work of kernel 2. So logically you can think of it like this. If the block ID is less than some x, it does the work of kernel 1. If not, it does the work of kernel 2. So yeah, the way we distribute computation is among different blocks and for independent kernels with similar computation time. Why is that? Otherwise your different blocks may again take different amounts of time and you have no control over how these blocks are going to be scheduled, right? So you could have one of kernel's 1's blocks running with kernel 2's blocks, and those may take different amounts of time, again causing issues. So again, if they have similar computation time, it's great to use this method. Now here, how do we come up with the threads and blocks? The blocks would be the sum. So this is again easy to understand. So this is where you're distributing the computation. So you have to have the blocks as the sum of number of blocks in kernel 1 and number of blocks in kernel 2. Whereas the threads, you just take it as the maximum of the two. And again, if the workload of blocks differs a lot, this method is not suitable. So pictorially, if you had to look at it like this, so here you can see that the number of threads is different for K1 and K2. And the number of blocks is also different. But blocks, we just take sum of the two. So there are 4 for kernel 1 and 6 for kernel 2. We take it as is. Now coming to the threads, you have max of 2 and 3, which is 3. So you take it as 3. But the kernel 1 uses only 2 threads. And the kernel 2, so this will be idle in a sense. And kernel 2 uses all of the 3 threads per block. So that is inter-block fusion. Now we look briefly at coarsening and then we'll move over to the questions. But before that, any doubts in the various fusion techniques? Is something not clear? Okay, if not, let's keep going. So thread coarsening. So you may be doing some redundant memory accesses and some redundant calculations when you're doing this parallel execution. So you could merge multiple threads into one. And this allows overcoming these limitations. You could reuse results, you could avoid doing redundant work. So this is similar to loop unrolling but applied across parallel threads. So again, this is a very common compiler optimization. You could look it up. It's not a very GPU specific thing. But in the GPU world, this is just applied across parallel threads rather than serial loop iterations. So we won't go into a lot of details on this here, but we will discuss some of these in the questions. Thread coarsening results in reduction in parallelism. Beneficial effects, you require lesser number of threads to be launched. Barrier execution is reduced, and increased number of instructions increases scope for exploiting hardware level, instruction level parallelism. So yeah, with that we come to the problem solving part of it. Okay, we have a question. It was mentioned in the lecture that thread coarsening leads to sharing of local memory, but since each thread has its own registered memory which only that thread can access and no other thread can access, how can that register be shared among different threads? Yeah, we'll take up this question maybe after we solve some of the questions on coarsening or in the next session, depending on how much time we have left. But thanks for the question. Any other doubts? Okay, if not, let's start with the problems. Okay, consider two independent CUDA kernels as given below to be run on a target GPU with 32 SMs and each SM supporting a maximum of 2048 active threads per SM. Assume that there are as many SFUs as the number of active threads per SM. The kernel launch parameters are 1024, 1024 for both of them. The descriptions are given below. Kernel 1 TID equal to threadidx.x. If the TID less than 512, out1 of g underscore TID equal to in1 g underscore TID plus in2 g underscore TID. Else you do a addition but on the sine and the cos of those same two terms. This is your kernel 1. Kernel 2, again the TID is the same and the condition is also the same, less than 512, but here your out2 is sine of in1 plus cos of in2, and in the else your out is simply the sum of the two. Now each float type sine or cos operation takes 20 cycles and each float addition takes 4 cycles. Ignore any penalties incurred due to memory accesses and data transfer overheads. Now calculate the total number of cycles it will take to compute the inner thread fused version of the two kernels. Consider execution time only due to sine, cos and addition operations. So you have 4 options here for the total number of cycles. So yeah, this is the kernel description. I'll pause here for a bit and then go to kernel 2 again. You can take a couple of minutes to solve this. Okay, 1536. Yeah, this is the other kernel. Again, 20 and 4. I'll go to the options now and give you maybe 1 more minute for people who are still solving. Anyone else? Okay, maybe we'll solve this question and the next one will be easier for you. If you need more time, let me know. I can wait. But if not, we'll just discuss the answer. Okay, so let's discuss the answer. It is B1536, but let's see how, right? So now, first of all, we are going to do a inner thread fusion of the two given kernels. So for the fused kernel, first we need to calculate how many cycles it takes in a given block, right? So let's look at this. It says 20 cycles per sine and cos operation, and addition takes 4 cycles. So this is going to take you 4 cycles. Here you have one sine and one cos operation, which takes you 2 into 20, 40, and you have an addition. So this is going to take you 44 cycles, right? And going back to kernel 1, it is the same thing except that it's reversed. So this is going to take you 4 and this is going to take you 44, right? Now, when I fuse it, it's going to be sort of these two combined, as in L of TID less than 512. So all threads with IDs less than that are going to do both of these two operations, and everything that's greater is going to do both of these operations. So the sum of the two is going to be 44 plus 4, right? So you have 44 plus 4 twice. Now why is this twice? Because again, when we have this sort of branching happening, it's going to be serialized, right? So you have 4 plus 44 and 4 plus 44, which becomes 48 plus 48, which is 96. Now this is going to be in a single block, right? But what you are asked is the execution time of the kernel itself. So we need to figure out, we know how many blocks there are, right? Based on the launch parameters. The launch parameters are given as 1024, 1024 for the individual kernels. Now, if you remember inner thread fusion, let's just go back to it. Yeah, if you remember, we just take the max of the two, right? So the new kernel will also have the launch parameters as 1024, 1024, right? So you know that the number of blocks is going to be 1024 for the fused kernel also. Now, what we need to figure out is how many batches will there be, because a certain number of blocks are going to execute in parallel at any given time. So you need to figure out, and this is going to take you 96 cycles, right? So you need to figure out how many such batches of blocks will be executing. So that's what we are trying to do here. So out of 1024 into 1024 overall threads that you have, you have to look at the architectural constraints here. It has 32 SMs, and each SM can support a maximum of 2048 active threads. So the number of batches is given to you by 1024 into 1024 divided by 2048, that is the number of threads per block, the maximum number of threads per block, into 32 SMs, which gives you 16. So you will have 16 such batches happening in order for the fused kernel to finish executing. So now the total number of cycles it takes will be this 96 into 16 for all the batches basically. That will give you 1536, and that's why the answer is B. So I think this involves concepts not just from this week but also the previous weeks, right? It builds upon a lot of things. For instance, how many such batches are there, and if you have a certain number of SMs, then how do you make use of that? And then your notions of warp divergence, and then execution time, and things like that. So it may have been a little tough, but as we solve one or two questions, you will kind of get familiar with this. I'll just wait here for a few seconds before moving to the next one. Look through the solution. If something is not clear, let me know. Okay, if not, let's look at the next question. Assume that blocks are scheduled in a round robin fashion to the underlying hardware. Block 0 is mapped to SM0, block 1 is mapped to SM1, etc. Calculate the number of cycles it will take, again only due to sine cos add, to compute for the inter-block fused version of the two kernels. You have four options. This one should be hopefully a little easier. The only change is that you have an inter-block fused version now. Take a couple of minutes to solve this and then we'll discuss. It should be the same 1536. Okay. Anyone else? Okay, we have one more answer, 1536. Anyone else? Okay, let's discuss the answer. It is 1536, but let's talk about how. So, unlike in the inner thread, now we are going for inter block, meaning that let's take a quick look at inter block for those of you who don't remember. If block ID is less than a certain value, it's going to be doing the kernel 1 work, if not the kernel 2 work. And how do you get the launch parameters? Threads would be max of the two and blocks would be sum of the two, right? Now with that in mind, let's come back to this question. So the launch parameters is going to be, so this had 1024, 1024, 1024, 1024. So the blocks is going to be the sum of the two. The number of threads per block is going to remain the same because it's the max, right? And if it is a certain, if it's less than 1024 blocks, it's going to do the work of kernel 1. If not, the next 1024 blocks will do the work of kernel 2. Now, as we calculated previously for the if and else part, the total number of cycles that it takes is 44 plus 4, both for kernel 1 and kernel 2. Right? This part I hope is clear. Now, we also know that out of the 2048 blocks, the first 1024 blocks do the operations for kernel 1 and the next 1024 blocks do the operations for kernel 2. Now, with the assumption given in this question that block 0 is mapped to SM0, block 1 to SM1, so on, with that, only with that assumption we can solve this, right? That's something to note carefully. So, then what happens is in the first how many ever batches, so how do you calculate this? So, again, you have a total of 1024 multiplied by 1024. Architectural constraints remain the same, right? You have 32 SMs, you have 2048 threads per block, both are architectural limits. So it takes you 16 batches to finish the work for kernel 1, right? That's why we are taking 1024 here, not 2048. We are trying to find out how many batches it takes to finish the work of kernel 1. After that, we separately look at the work for kernel 2. So we get that it's 16 batches and we know that the cycles is going to be 48, right, per block. So the total time for the kernel 1 blocks is 16 into 48, which is 768. Similarly, now you have the next 1024 blocks which are going to do the work of kernel 2. Again, how many batches is that going to take? Same calculation as before. You'll get 16 batches. And this also again takes the same time because again both kernel 1 and kernel 2 have the same number of cycles per block. So this is going to take another 768 cycles. So the total time that the fused kernel takes is 768 plus 768, which is 1536. Again, this is a bit complicated, so I'll just pause here for a minute. Please go through this. If something is not clear, let me know. Even if at a later point in the week you watch the live session video and something is not clear, please feel free to ask on the discussion forum, right? You need not wait till the next week's live session. Then I can look at it and answer it within a day or two and also discuss it in the next week's session. Okay, we have a doubt. If similar problem was there for inner block, okay, then we take the maximum number of blocks and threads as sum of both kernels. Yes, okay. So do we compute it the same as question 1? That is the number of batches, not twice. Let me think about that. Yeah, the first part of what you say is definitely correct. That comes from the inner block definition itself. So threads would be sum, and then blocks would be max. That is correct. Now, yeah, so because you're launching it in this way, right? It is going to be only once the number of batches that you calculate. And within a block, depending on the thread ID, as we see here, it may be doing the work of kernel 1 or kernel 2. So the number of batches calculation would be only once. That's correct. Yeah, there is only one batch after fusion. That's also correct. Any other questions? So here that calculation in 2 steps comes because we are explicitly told this also. So therefore we are trying to calculate when kernel 1 blocks are executing, how long does it take, and when kernel 2 blocks are executing, how long does it take separately. But in the inner block case, you're just going to have threads doing the different work, right? So it's not going to have a 2-step calculation as such, because the block itself is used to parallelize the computation. So how many batches it takes would be only a one single calculation. Hope that is clear. Great. Okay, we'll do a couple more questions and then maybe take a break. Okay, these are relatively easier. So these involve your knowledge of what the fusion method is and how you come up with the launch parameters. So I think all of you should be able to answer this. Consider the kernel specified with modified calling parameters 1024, 512, 512, 1024. What will the kernel launch parameters for an inner thread fused version of the two kernels be? We have 4 options. We have one answer, C. Okay. Anyone else? C. Okay. C. Anyone else? Any other answers? Okay, we'll look at the answer. It is C, and I think this is quite clear. So for inner thread fusion, we just do a max for both threads and blocks, right? So for both, the max comes out to be 1024, which is C. That's the answer. Any doubts here? Okay, let's move to a similar one. Now you have kernel 1 1024 1024, 2 as 512 1024. For an inner block fusion, what are the launch parameters? C. Okay. Anyone else? C. Okay. So if you don't remember how you come up with these values, I think what would help is for you to at least remember the three different things pictorially, right? Once you are able to do that, you'll be able to come up with the answer. Let me discuss this answer and briefly tell you how to do that. So answer is C here. Again, if you remember the formula, it was just sum of the threads and max of the blocks. So you get 1024, 2048. But what I am trying to tell you is remember this pictorially. For instance, if you think about inner block fusion, you just need to remember this part, right? This small diagram here, that within a block, some threads are going to do the work of kernel 1, some threads are going to do the work of kernel 2. The moment you remember this, it's very easy to realize why your number of threads per block needs to be the sum of the two, and the other one is max, right? Similarly, if I ask you about inter-block fusion, all you need to remember is this picture where different blocks work on kernel 1 and kernel 2. Therefore, intuitively, you can come up with the logic that, okay, my total number of blocks for the fused kernel needs to be the sum of the two individually. Number of threads is the max. And if I tell you inner thread, then you remember this. So you know that there is no change in either of the dimensions. So you just take max of the two, right? If you can remember this picture and this logically associate this with it, I think answering this sort of questions will be very easy. You don't need to remember the formula or the launch parameter definition itself. Just remembering what it is logically should help you. So okay, so that's why for 4 it is C, right? It's sum of the threads, because if you remember inner block fusion, you're going to have some threads in the block doing the work of this kernel, some doing the work of this. Therefore, the total number of threads per block that you need will be 1024 plus 1024, 2048. The other dimension is just the max of these two, just 1024. So that's the answer. We'll do one more in this pattern. Consider the kernel with 512, 512, 512, 1024. Launch parameters for an inter-blocked fusion. This one you should be able to do, especially after we just discussed this. We have one answer, C. Okay. Anyone else? C. C. Okay. Let's look at the answer. It is C1024, 1024. So like I said, for the inter-blocked fused version, you need to remember that some blocks do the work of kernel 1 and some blocks do the work of kernel 2. Therefore, your number of blocks would be the sum of these two, which is 1024. And along the other dimension, you just take the max, right? So that would be 1024 again, and this is your answer. Any doubts here? Okay, if not, we will take a 5-minute break now, and also come up with a list of any other doubts you have. We can look at it after the break. So we'll resume at 7:06. Okay, let's continue. So, next question. Consider the features of a given GPU architecture: streaming multiprocessors 20, max active threads per SM 2048, threads per block 32, registers per SM 64K, and max shared memory per SM 128 KB. Now, the given kernel performs transpose of a given data set without any coarsening. So tile dimension is 32, block rows is 32. This is your kernel. So float tile dimension in both sides, and x equal to block idx dot y star tile dimension plus thread idx dot x, y equal to block idx dot y star tile dimension plus thread idx dot y, width equal to grid dimension dot x into tile dimension, and in a loop where j goes from 0 to tile dimension and gets incremented by block rows, tile of thread idx dot y plus j and thread idx dot x equal to I data of y plus j star width plus x. You have a sync threads after that, and then x equal to block idx dot y star tile dimension plus thread idx dot x, y equal to block idx dot x star tile dimension plus thread idx dot y. Now you have a for loop again, which goes from 0 to tile dimension, gets incremented by block rows, and O data of y plus j star width plus x equal to tile of thread idx dot x, thread idx dot y plus j. This is your kernel code. Now the question says launch parameter is given as follows: block is 32 32 1, grid is 64 64 1, and this is your kernel call. Now calculate the optimal coarsening factor for thread level coarsening, assuming that the kernel is coarsened only across the x dimension. So I'll move back to this part and then go to the kernel. I'll move to the kernel now. Move to the launch parameters. Yeah, these are your options. You can let me know when you have an answer, then we'll discuss. Any answers? If you need any of the previous data, please let me know and I can scroll back. Anyone? Give you a few more seconds. Okay, let's go through the answer. It is 16. So we'll discuss this one in detail and hopefully the next one will be easier to solve. So again, we had a similar one in your lectures itself, but let's go through this. So we'll assume that X is the coarsening factor, and as a recap, we are trying to do thread level coarsening and we are doing coarsening only across the X dimension. Now your block size originally was, for the unfused kernel, for the uncoarsened kernel, was 32 into 32, 1024, right? Now your block size is going to change to 1024 by X. Why? Because we are doing thread coarsening, meaning that one thread is now going to do the work of multiple threads. So depending on what that X is, your block size will change, right? Now how many active blocks are going to be there per SM is what we are trying to calculate. So again, from an architectural constraint, you have the max active threads per SM as 2048. So that's what the SM can support, and now we don't know what is this X as of now. So we'll just substitute whatever we have there, which is 1024 by X, which ends up giving us the blocks per SM as 2X. Now for thread level coarsening, the shared memory requirement per block is going to be the same, because you're basically taking the work of two threads and maybe assigning it to one thread. But across the block, if you see, what happens is there may be fewer threads, but the work done or the memory requirement, both of these remain the same, right? So the shared memory requirement per block will be the usual 32 cross 32, which is because of your block dimensions, into 4 bytes, and this gives you 4096 bytes. This does not change with coarsening, so it's going to be the same. This is per block. What changes is how many blocks are you going to be able to accommodate per SM, because the block size itself changes now. So you know that the number of blocks per SM is 2x. So the shared memory requirement per SM is the number of blocks into the shared memory per block, which is 2x into 4096. Now another constraint we have is that the total allowed shared memory per SM is 128 KB. So we have 128 KB on one side, the KB is expanded as 1024 bytes, and on the other side we have 2x into 4096. So if we solve for this, we basically get X to be 16, 128 by 8, which is 16, right? So all you need to remember is that this block size changes in thread coarsening. So you need to recompute the number of blocks per SM in terms of the coarsening factor. The memory per block is going to be the same. Use that to compute memory per SM and use the memory constraint per SM that's given to you. I'll pause here for a few seconds. Please go through this. again we have 2 or 3 more questions in a very similar fashion, right? So understanding this will help you solve those as well. Okay, if there are no doubts here, we'll move to the next question. Calculate the optimal coarsening factor for block level coarsening, assuming that the kernel is coarsened only along the x dimension for the same program. So your options are again 4, 8, 16 and 32. So I'll go back to the launch parameters. So to 64, 64, 1, 32, 32, 1, and here are your architectural constraints. So you're asked for the coarsening factor for block level coarsening now. So you have to try to solve it in a similar fashion that we just did, using the shared memory constraint, using the block size and so on, except that now you will have to use your understanding of block level coarsening. I'll go back to your options. Okay, maybe we'll solve this one too. So since these questions seem to be difficult for most of you, please go back and look at this after today's live session, and if you have any doubts or questions, please ask on the discussion forum, right? We'll look at the answer for this. It is C16. So again, we'll start out the same way, right? X is the coarsening factor, and yeah, you can do that. Now the block size again is the same, 1024. The active blocks per SM is now 2048 by 1024 2, right? Because this is your architectural constraint that you can have a maximum of 2048 threads per block. So that gives you 2 blocks per SM. Now what changes is this part, right? So here your shared memory requirement per block actually changes. It gets multiplied by the coarsening factor, because unlike in the thread level coarsening, we will discuss that the memory requirement per block remains the same, because there were 2 threads doing some work and now there's 1 thread doing the same work, right? So the same memory will be used, right? But here that's not the case, because you're combining the work of multiple blocks into one block. So the per block memory requirement is itself going to linearly increase as per your coarsening factor. So your shared memory requirement becomes 32 into 34 into 4 into x. We don't know what this x is yet. And now similarly you will calculate the shared memory requirement per SM, which you take this and multiply it with the number of blocks. That also remains same as the previous question. So you get 2 into 4096 into x. Again, the constraint you have from the architecture is max allowed shared memory per SM is 128 KB. So you equate the two. 2 into 4096 into x equal to 128 into 1024. So that again comes out to be 128 by 8, which is 16. This is how you calculate this. Any doubts here? Now, coming to the doubt that was asked on thread level coarsening, right? So, the doubt that was asked, as a quick recap, was every thread has its own register memory that only that thread can access and nothing else can access. So, how is the register shared among different threads? I think what is meant in that lecture is, now let's say I have two threads, right? Now, I'm going to basically make this one thread do the work of those two threads. So now this thread, in a sense, so it's not that the registers are being shared among two threads of the coarsened kernel, because you're doing this operation of coarsening, because the work done by these two threads are now done by this new one thread. In a sense, logically, it is like sharing the registers among these two threads. But I don't think the meaning is that two coarsened threads can now share registers. That's not possible, right? Like you said, registers are per thread. What is meant is that these two threads, instead of using the different registers now, because you're coarsening them or merging them into one thread, it is essentially logically equal to sharing the registers. Hopefully that's clarified. I'll also re-mention this in the next week's live session with a diagram or something like that. Yeah, good. Any other questions before we move to the next one? Okay, some slight variations. Consider the thread level coarsened version of the kernel with a coarsening factor of 4 and the target GPU is the same. Compute the total shared memory requirement per SM. So we saw how to do this in previous questions. Hopefully this one is easier. You just need to use the thread level coarsening way to solve this, and the coarsening factor as 4. Okay, we have one answer saying B. Okay. Anyone else? We'll give you a minute more, then we can discuss. Okay, let's look at how to do this. So the answer is B, 32,768, right? So let's go back to the question we solved on thread level coarsening. So that was question 6, right? So what you can do this in two ways. One is you can directly use this expression. So 2 into x into 4096 was what we derived as the shared memory requirement per SM, right? Now x in this question is given to you as 4. So 2 into 4 into 4096, which is 8 into 4096, which gives you 32,768. If you remember this expression, well and good. If not, like I always say, try to do it logically. Again, you have this block size as 1024 divided by x. Now x is given to you as 4, right? And then active block. So you can do basically all the calculation up till this point using this value of x. So your block size would be 1024 by 4, and your active blocks would basically come out to be 8. Then shared memory per requirement per block, this will not change, it will be 4096 bytes itself. Per SM would become 8 into 4096, which is again 32,000. So you can use either way. If you find it easier to remember expressions, you can directly use this. If not, you can derive this from first principles, right? So thread level coarsening, the block size changes. What is the new block size going to be? Then what is the number of blocks per SM going to be? Then shared memory per block, and then from there shared memory per SM. That's all you need to do. We'll solve one more question in this pattern. I'll pause here. There are any doubts or questions, feel free to ask. Okay, we'll move to the next one. It's a very similar question. Consider the thread level coarsened version with a coarsening factor of 16. For this, compute the shared memory requirement. Hopefully this one is easy given that we just did the last one. Okay, we have one answer C. Anyone else? C, okay. Okay, let's look at the answer. It is C. Again, like I said, you could calculate this in two ways. directly use the formula 2 is into 4096 into substitute the coarsening factor as 16. If not, what you need to do is compute the new block size, which would be 1024 by 16. Then you would compute the active number of blocks, which is 2048 divided by 1024 by 16, and then you would compute the shared memory per SM, that would shared memory per block, which would remain the same, and then you would compute the shared memory per SM. So you would ultimately end up getting the same answer. C. So hopefully this pattern of questions is also clear. We'll move to one last question that is slightly different. Okay, for an effective thread level coarsening across x-axis for a 2D kernel with launch parameters 16, 16, 1, 32, 32, 1, coarsening factor of 4 and target platform with warp size 6, the bounds for stride length are, so basically like the min and max, these 4 options. So you can take a couple of minutes and then we'll discuss this. Anyone? We'll wait a minute more. We have one answer, D. Okay. Okay, we have one more answer saying B. Okay. 8, 8. Okay. Anyone else? Okay, if not, let's look at the answer. So the answer is B88. So if you remember from your lectures, the max and the min stride lengths were calculated like this. The min stride length is greater than equal to the warp size to ensure memory coalescing, right? You want the axis is, as we studied in I think week 5 or week 6, we want the memory axes from a warp to be coalesced. Therefore, you want the stride length to be greater than equal to the warp size. Warp size is given as 8, so this would be your minimum bound. Now your maximum stride length is bounded by number of threads per block in the dimension where the coarsening is applied divided by the coarsening factor. So in this case, that is 32 by 4, which gives you 8. So the min and max are both 8. Now coming to why is this needed, right? Let's take a simple example. Let's say we have 32 threads, right? 0 to 31. Now I'm trying to use a coarsening factor of 2 and do thread level coarsening, which means that I want to combine the work of 2 threads into 1. Now I could have a stride of 1, meaning I could combine 2 thread IDs which were offset by 1. By the way, for the initial doubt that was asked, right, the difference between stride and coarsening factor. Coarsening factor is how many threads work you're going to combine into 1. So when I say coarsening factor of 4, I'm combining the work of all these 4 threads into the work of 1 thread, right? Whereas stride is how I combine. Which 4 threads do I pick to constitute this coarsened 1 thread? That's the difference between the two. Now coming to the stride length, like I was saying, if I have a coarsening factor of 2, I'm going to combine 2 threads, right? So those 2 threads could be 0 and 1. They could be 0 and let's say 9. They could be 0 and maybe 15, right? So how can I set limits on that? If I want to have a coarsening factor of 2, then what is the maximum stride length I could have? So going by this formula, it would give us 32 by 2, which is 16, meaning that the maximum offset I could have between, or the stride length I could have, has to be 16. So let's say I took it as maybe 18, right? So let's say I'm combining 0 and 19. Now what happens when I reach maybe 14 or 15? I can't effectively combine because I'm going outside the limits of this thread block, right? Basically this bound lets you use a coarsening factor that you want while ensuring that that works for that block size. That's all it is. So if you think about it logically, you'll understand. So you want to now combine every 4 threads in this 32 threads to form overall 8 threads, right? So what is the maximum distance or the stride between them you can have? You can have a maximum stride of 8, because any more than that and you will end up going outside the limits of this block. That's why the second limit exists. So both of those are 8. And hopefully the difference between stride and coarsening factor is also clear now. Great. Okay, I think we're at the, I'll pause here. If you have any doubts, you can ask me. I think this is the last question. I think this set of 10 questions covers almost all of the patterns of questions I have seen in the assignment so far. Okay, if the coarsening factor is 4, they will be from 4 different warps. Yes, here the warp size is 8, and it depends on the coarsening factor and the stride length that you have, right? So if the stride length is taken as here, so both min and max come out to 8, that means that your stride length has to be a minimum of 8. So as you're saying, it will be from 4 different warps. But in other cases where maybe the stride length is just 1, then even if the coarsening factor is high, they need not come from different warps. They could come from the same warp. So it's a combination of both the coarsening factor, the stride length, and of course the warp size that that particular architecture is using. Okay, so yeah, I think we are done with the questions for today. So thank you so much for joining and keeping it interactive. If you have any doubts on any of the questions that are solved here, please feel free to ask in the discussion forum. If not, and if you have any other doubts now also, please post it on chat. I'll be here for a minute more. If not, thank you so much and see you next week. Thank you. Thank you. Thank you.